This video is part of our series on teaching geometric algebra at the high school level, and it addresses the concern that's shown here in the left-hand picture that adding unlike things, for example, a scalar and an area, can look like weird magic to students. And notice adding. We want to address that issue here. So this video is especially for prospective high school level geometric algebra teachers and advocates of geometric algebra who want to make the case for it to such teachers. And a source document for this video, which will be linked in the video description, is this one on teaching of the geometric product or its dimensionality. And what we will see in this video is an exploration of the dimensionality of the geometric product in a way that will, first of all, address students' potential objections to adding unlike things, and will also be of lasting benefit to science students in general. What do we mean by dimensionality? Well, the variables in science equations have dimensions like length, mass, and time. And why is the exploration of geometric algebra's dimensionality necessary? Well, as Professor Walter Whiteley, who is an advocate of teaching students to see like mathematicians, has pointed out, and I will link his paper in the description, math can look like a sort of weird magic to students who aren't trained to see what's going on in equations. So students need to be trained to see what's happening in geometric algebra equations, just as in any other. And here's where we run into the need to explore geometric algebra's dimensionality. What students will see in geometric algebra equations is an addition of unlike things, a scalar and an area. And again, the idea of an addition. And this idea here violates something that students have learned about dimensionality, that only likes can be added to likes. Therefore, unless students see have been given an exploration of geometric algebra's dimensionality, the geometric algebra or the geometric product can look like weird magic even to trained students, or perhaps especially to students who have been trained to see what's going on. And what is the lasting benefit of exploring geometric algebra's dimensionality? Well, dimensionality is a big difference between math as used in science and math as taught in math classes. And the noted educator Redish wrote a series on using mathematics and physics where he emphasizes this point. I'll present the link for this page in the video description, but Redish wrote a 7-part or 8-part series on the tools of math that are used in physics. And he made dimensionality the subject of the first part of that series. And in your own time you might look at this a bit. So anyway, that's why teaching the dimensionality of the geometric product could be of lasting benefit to all students. Dimensionality in general is important if we can present it in the context of the geometric product. We're killing two birds with one stone and making a virtue out of a necessity. Also, an exploration of geometric algebra's dimensionality will give students a more sophisticated definition of what an algebra is, in its modern sense. So, our exploration of geometric algebra's dimensionality will treat, first of all, the more sophisticated understanding of what an algebra is. We'll look at the dimensionality or the dimensionality of the geometric product of two geometric vectors, which I will call u and v. And we'll also explore how dimensionality evolves during or in the course of using the geometric product to solve a typical problem, meaning, or the problem is, if we know the inner product of an unknown vector with a known one, and also the outer product, how do we find this unknown product or this unknown vector? Typical problem. So, exploring geometric algebra's dimensionality. What is the dimensionality of these two components of the geometric product? The inner product and the outer one. Well, the geometric vector rather, such as the ones we're treating here, has dimension L, length. So both the inner and the outer product serve dimension L squared. Why is this? Well, the inner product is a product of, the length of one vector here with the projection of the other one upon that. I could have phrased that differently, but I think you all are familiar with this idea. In contrast, the outer product is an oriented area, like the area of this parallelogram that's formed. So both of these components here are of dimension L squared. As we just mentioned here. But now, what is the nature of this operation that is represented by the symbol plus, just like addition? Well, we'll answer that question, which has caused problems for a lot of people or a lot of critics of geometric algebra, by examining first of all what is an algebra. And we will be we will be citing the text from Hestena's book, New Foundations for Classical Mechanics. So, understanding of what an algebra is. In what sense does GA add a scalar and a bivector? I'll just let you read this on your own here for just a moment or two. So the most important thing to get from this passage is that the geometric product is an invention with a certain purpose. And that purpose was to capture all of the information about the relative directions of two vectors. He called them A and B. We're using U and V here. So as we saw earlier, the inner product has to do with the parallel, or the product of the parallel component or the parallel components of the two vectors. The outer has to do with the perpendicularity. So again, this geometric product was designed for that purpose, to capture all the information about the relative directions, and this is how it gets that done, by combining these two pieces of information. But what is this thing here? This plus, this sum? Well, now we'll go into what is an algebra. Grassmann, who is mentioned here, was one of the originators, or one of the two inventors of geometric algebra. And as Hestenes mentions, Grassmann was the first person to arrive at the modern conception of algebra as a system of rules relating otherwise unidentified entities. So he realized that the nature of the outer product, and well, of the inner product, could be specified by the rules that it obeys. And that applies generally to the geometric product as a whole. So, as Hestenes goes on to say here, this abstract Grassmann fashion of defining an algebra has become standard. I'll let you read the rest of this. So the mathematical meaning of adding scalars and bivectors is determined by specifying that this addition, so-called, satisfies the usual commutative and associative rules. So again, it would not matter what we called that operation or what symbol we used to represent it. We could have drawn a little bunny in there instead of the addition symbol and called that addition whatever we wished, and we would still use it and it would still have the same properties. So let's not get hung up on this idea of forcing that operation and the idea of an addition. And I think we can do our students a service if we explain this well as Heston has by referring to what an algebra really is now, or what its modern definition is. So let's put that behind us. And now look at geometric algebra's dimensionality in the context of solving a typical problem. The one we mentioned earlier, finding an unknown vector u if we know u dot v, u wedge v, and v itself. Now, the first thing we're going to look at is that these quantities that are written so neatly and so economically here can take on fairly ganglious, to use an expression, forms when we solve a real problem. For example, this older video on our channel solved a certain tangency problem, and you see the vectors p, c, and such here. Now, and also the tangent vector here. Let's take a look at what these vectors and their dot and wedge products really look like in this context. This is what it looks like, but what we have here is the inner product of one vector with, this all evaluates to a vector is equal to something here, and the outer product of that same vector with this thing is, well, we see it here. So what we write neatly as u dot v and u wedge v can take on some fairly gnarly looking forms there, but that's all they are. In their essence, they're just u dot v and u wedge v. So let's move beyond that. Now, we're citing here from that source document that I showed earlier. So we want to study the dimensionality of the geometric product in the context of finding, well, you can read this. Now, we're not going to show how to solve that problem. What we're going to do is examine how the dimensionality evolves during the procedure. So here we write, what amounts to the definition of the geometric product of u and v. Now, to solve for u, we're going to multiply on both sides by the multiplicative inverse of v. That undoes the multiplication by v and leaves u, and of course the geometric, or operation that we call addition has the distributive property. So this factor here just distributes, and now we get u dot v times the inverse of v plus, this should be a u wedge v here, apologize for that, times the inverse of v. And so now formally we have the solution. But again, looking at the dimensionality, what is going on here? This term, or this factor u dot v, has dimensionality L squared. U itself is just of dimensionality u. And so what is the dimensionality of the inverse of v? Of course, I should mention that this is supposed to be a u wedge v, and that also has dimensionality L squared. So what is the dimensionality of the multiplicative inverse of v? Again, this is something that the students might balk at, what is going on here. So we want to be able to show that to them, and it will be of lasting benefit. So, okay, let's find out the dimensionality of the inverse by looking at the definition of that inverse. Okay, here is the definition. So the vector v of dimensionality L is divided by v squared, or the square of the magnitude or length of v, which is L squared, or dimensionality L squared. So the dimensionality of v to the minus 1 is 1 over L, not L as itself as it would be for a vector. But the inverse of v does act like a vector when multiplied by scalars and vectors and by vectors in equation 2. Or does it? Does it really act that way? Well, let's look at that. And again, for the benefit of the students. So to see what's really going on here, we will rewrite our solution for u, which was, well, you can read it here, and again, that should be a wedge. I apologize. We'll write that using or substituting the definition of the multiplicative inverse of v. And now we will distribute that square, as we show here, and we end up with u dot v, or u dot unit vector v, times unit vector v, plus u wedge unit vector v, times unit vector v. Now, what does that mean? Well, okay, now what we have here, this factor is of dimension L, just like u itself is, and so is this. So v, or the unit vector v, is dimensionless. It just gives a direction. And I'll just let you read through this by yourselves. So this is a diagram of how that solution, or how this equation expresses the unknown vector u as a sum of two vectors, these two vectors. So again, our purpose in doing this was not to show how to solve such an equation, but to show how the dimensionality evolves. If you want to find out how to solve such things, there are other videos rather on our channel. So go ahead and read that for a bit. Now, as a summary, I'll let you just read that also. I hope this video has been useful. I want it to be genuinely helpful for students and teachers. So please be free in your comments and criticisms. We want to produce materials that are really going to help the teaching of GA at the high school level. And if you are interested, I hope that you'll consider joining the LinkedIn group that is dedicated to preparing such materials. So I will link that also in the video description. Thank you for your time, and I look forward to your comments.